So having said that, I want to get started on Chapter 3, since all of you that are here undoubtedly passed the entrance exam, which was based on Chapter 2. And this chapter, Chapter 3, which actually starts on page 40 of your text, is entitled Chemical and Physical Features of Seawater and the World Ocean. And I'm really not going to talk about the oceans right now, but I do want to talk about not necessarily seawater, but water as a chemical entity, some of its chemical properties and some of its physical properties. Some of these things are mentioned in the book, but some of them are not necessarily clarified, and I'd like to give you perhaps a little bit more information. So the first thing that I want to mention actually has to do with low molecular weight chemical entities. And there aren't a whole heck of a lot of these kinds of compounds, but if you think about the things that immediately come to mind, things like ammonia or hydrofluoric acid. When I say low molecular weight, I'm talking about specifically compounds that have molecular weights under 50 atomic mass units, and some of them are even smaller than that. So if you look at compounds of that nature, you will find that almost invariably at ambient temperatures, these things are going to exist in the form of gases. It's unlikely that you're going to find, there are a few that will be liquids, but you're not going to find any compound that is going to be a liquid over as wide a range as water is, and something that will actually have the set of properties, the unique set of properties that make water so special in terms of its ability to sustain life. So for people that walk around and say that they don't believe in God, I find it hard for someone to actually take that attitude, because you can see in the simple molecule of water, you can really see the work of Hashem, because the properties of this molecule are so special, and it is such an individual molecule that there is nothing else that could possibly sustain life in the way that water does. So I see the hand of the Creator in actually forming this molecule, because it as I say, the properties are such that if any particular thing were changed, life would not have been possible. So we're going to look at some of the properties of water. As I said, these very low molecular weight compounds tend to be almost invariably gases at room temperature. Water has an atomic mass of 18. Ammonia, which has an atomic mass of 17, has a melting point of minus 78 degrees approximately, and a boiling point of minus 33 degrees. This is Celsius. So these things, this of course is a gas at room temperature. It's a gas all the way down to minus 33 degrees where it liquefies. Hydrogen sulfide, which is a lot closer to water, because it's really more analogous to water, because it has two hydrogens, as water does, and the central atom is sulfur, which is a chalcogen, just like oxygen. It's in the same group, group 16 of the periodic table. Sulfur has two unshared pairs of electrons, as does oxygen, but hydrogen sulfide has much different properties than water does. Its melting point is minus 82 degrees. Its boiling point is minus 60 degrees. So again, hydrogen sulfide is going to be a gas at ambient temperature, and actually hydrogen sulfide is really quite toxic to most forms of life. Then if we look at another low molecular weight compound, hydrogen fluoride has an atomic mass of 19. Its melting point is minus 84 degrees, and it boils at 19.5 degrees Celsius. So again, at what we would consider to be room temperature, which is 20 degrees Celsius, we would expect hydrogen fluoride to exist as a gas. Now we can look at some other compounds that have an OH group like water does, an oxygen and a hydrogen. And if we pick a compound like methanol, which is a carbon with three hydrogens attached to it, a methyl group, a CH3, and then there's an OH, we find that compound has properties, has some properties that it shares with water. Its atomic mass is 32, so it's almost twice as has almost twice the atomic mass of water. It melts at minus 97 degrees, and it boils at approximately 65 degrees Celsius. So it is actually a liquid over a fairly wide range of temperatures, but it still it turns out that for most forms of life, methanol also is very, very toxic. And if we take methanol and replace that hydroxy group with another methyl group, with another CH3, then we get something that has an even higher atomic mass, which is called dimethyl ether, CH3OCH3. This has an atomic mass of 46. It melts at minus 139 degrees. It boils at minus 24 degrees. So again, it's a gas. Carbon monoxide, another gas, has a molecular weight of 28, melts at minus 205 degrees, and boils at minus 192 degrees. So that has a very, very low boiling point. Carbon dioxide, which has a atomic mass of 44, melts at minus 78 degrees, and it boils at minus 57 degrees, but only at 5.185 atmospheres. Below that pressure, carbon dioxide does not even exist in the liquid state. So as they say, water should be a gas, but it's not, and the reason why has to do with hydrogen bonding, and it has to do with the unusual geometry of the water molecule. Let's look at carbon dioxide first, because like water, it consists of 3 atoms, but these atoms are doubly bonded to the carbon atom with double bonds. Water, which has an oxygen and 2 hydrogens, and these bonds, for those of you that may not have yet had chemistry, represent pairs of electrons. So this would be 2 pairs of electrons, this would be 1 pair of electron. These are what are called covalent bonds. So this is bonding in the water molecule, bonding in the carbon dioxide molecule. Carbon dioxide is a gas, as I said before, but it is a linear molecule. I've drawn water as though it's also a linear molecule, but in fact it's not, because it has these unshared pairs of electrons, and these actually force the molecule out of linearity. So instead of having a 180 degree angle from here to here, the actual angle, water would look more like this, and the actual angle in here is about 104.5 degrees roughly. If this were a tetrahedral angle, it would be closer to 109 degrees. So it's somewhat smaller than a tetrahedral angle, 109 degrees 28 minutes. This is about 5 degrees smaller than that. But nevertheless, there is this angle that forms here, and because of the unshared pairs of electrons here, we have a partial negative charge on the oxygen here, and even within the covalent bond here, even though the electrons are being shared by the hydrogen and the oxygen, because of the electronegative, the oxygen atom being more electronegative, it's kind of like when you're asked to share things with a little brother or sister, you don't necessarily share them so that it's 50-50. You may get since you're bigger, you may get a larger share of the pie. So, and that's what's actually happening with the oxygen. The oxygen being more electronegative, the electrons tend to be pulled here more to this side of the molecule. So this is negative here. The hydrogens, on the other hand, have a partial positive charge. And because of that, we say that water is a dipole. And you can actually demonstrate this if you want to in your kitchen or in your bathroom, just by running your spigot on a very slow stream of water. And then if you take a comb and you start combing your hair with the comb, you can pick up a static charge in the comb. The comb will actually have excess electrons on it. So your comb will be negatively charged, and if you hold that towards the stream of water, the negative charge will actually repel the negative charge of the oxygen atoms, and will push the stream of water away from you. So you'll actually see the water being bent away from the comb. So it's kind of an interesting thing to observe, but it does demonstrate this dipolar nature of the water molecule. And the other thing about this water molecule being dipolar like this, these molecules, in association with other water molecules, because of course they don't exist by themselves, but there are many, many water molecules all together, and these molecules, I didn't actually draw this one the way I wanted to. Let's redraw it. I'm going to put an oxygen here, a couple hydrogens out here. These water molecules will actually, in proximity to a neighboring water molecule, in addition to these covalent bonds, we get a weak bonding due to the fact that we have a partial negative here and a partial positive here. And we don't draw that with a solid line. We use a dotted line or a dashed line, something like this, to show that we actually have these weak bonds forming between the oxygen and the hydrogen atom. They're approximately 5% of the bond strength of the covalent bond that holds the oxygen to the hydrogen, which means that they can be broken, but we have to put some heat, some thermal energy in there in order to break those bonds. So this is what we refer to as hydrogen bonding, not to be confused with the bond between the oxygen and the hydrogen, which is a covalent oxygen-hydrogen bond. But when we talk about hydrogen bonding, we're talking about the bonding between hydrogen atom and an oxygen atom. There are other atoms also that will do this. Nitrogen will do this. So if you have an NH2, that can also bond to an OH. And if you have something that looks like this, which is called a carbonyl, this oxygen doubly bonded to a carbon atom can also hydrogen bond to a neighboring hydrogen atom. Anyway, it's this property of hydrogen bonding, which is very, very important, and is also one of the reasons why water has the particular set of properties that it does. Now, one of the things about water, because of this unusual hydrogen bonding phenomenon, and you can actually see this if you turn in your book